PyTorch. PyTorch is an open source machine learning library based on the Torch library, used for applications such as computer vision and natural language processing. Primarily, it was developed by the Facebook's AI Research Lab. It is a free and an open source software released under the modified BSD license. So, what is PyTorch for our understanding? It's a Python based scientific computing package targeted at two sets of audience. The first one being for the replacement of NumPy to use the power of GPUs, and the second one being a deep learning research platform that provides maximum flexibility and speed. What is tensor in PyTorch? A PyTorch tensor is basically the same as a NumPy array. It does not know anything about deep learning or computational graphs or gradients, and is just a generic n-dimensional array to be used for arbitrary numeric computation. The biggest difference between a NumPy array and a PyTorch tensor is that a PyTorch tensor can run either on either CPU or GPU. To run operations on the GPU, just cast the tensor to a CUDA data type. Training model in PyTorch. To train a model in PyTorch, we load the required classes and modules. We use the import statement to import the Torch library and then import torch.nn as nn, which is neural network. Then we import the functional component of the neural network in torch as f. We import torch.optim as optim to set the optimization. Then we import numpy to manipulate the arrays. We import torch vision to process the data and use the existing models. We import the OS and the copy to save the best model and get the data files. Image transformation. We need Using PyTorch, we can transform the images, changing the sizes of all images to an unanimous value, converting them to a tensor. Tensor transfers the values from scale 0 to 255 to 0 to 1. The normalization of the images with the mean and standard deviation for RGB values. We use the data transforms to train the transforms and compose them, to resize them, to convert them into tensors, and to normalize them. We use the validation to compose the transforms, to resize, to transfer them into tensors, and to normalize the same. Image normalization. After converting the images to tensor, every pixel value is in the range 0 to 1. Then, for every pixel, we apply the following formula to each of the channel values, and the ranges will now be from -1 to 1, inclusive of the ranges. The pixel red value minus the red channel mean divided by the red channel standard deviation would give a value of pixel red value minus 0.486 divided by 0.229. And similar calculations are performed for the green channel and the blue channel. Why do we need image normalization, you may ask? In general, in order to handle noise in data, data can be transformed globally to change the scale or range of data, that is, normalize the data. In convolutional neural networks, if we don't scale, that is, normalize the values, the range of different features, example image channels, will be different. Since the values are multiplied by the learning rate, the features that have larger scale might be overcompensated and features with a smaller scale might be undercompensated. In addition to the mentioned data reprocessing, in addition to the mentioned data preprocessing, there are some transformations that are used mainly for data augmentation. O transforms dot random horizontal flip flips the image horizontally so that both the alignments of the horizontal in the horizontal axis can be generated. O transforms dot random resized crop 224 resizes and crops the image so that different the images of different sizes can be resized to this particular frame and can be accessed. The data augmentation is a strategy that enables practitioners to significantly increase the diversity of the data available for training models without actually collecting new data. This is of specific importance when the dataset is contains a small number of values or the dataset is small. Data augmentation can increase the size of the dataset by performing horizontal flips of the images and resizing the images. Mini batch and epoch. Batch is the number of images which is propagated to a model iteration. An epoch refers to one cycle through the full training dataset. A particular model may have n number of epochs. Let us consider an example. The batch size being 4 and the number of epochs being 30. Let's take and in this example, let's consider that the number of images is 1024. The batch size is 4 and the number of iterations in every epoch is 256. We next load the data and set device. We load the dataset directory. We store the dataset directory under the name data underscore dir, and then we load the data using the image datasets and the data loaders. We then get the number of images and name of the classes of the images. The class names of the images are with respect to the trained dataset. We then set the device to either GPU mode or CPU mode. Sample network. Here is an example of PyTorch model. We have a class called sample network in which we use convolution, pooling, and other various layers necessary for the working of the PyTorch model. We first define all the layers of the model, and then we define a function to forward the forward function, which is called during the forward pass. Let's visualize the sample network in the previous slide. The different layers which have been declared in the model initialization are convolution layer 1, pooling layer, convolution layer 2, then we have the FC1 layer, FC2 layer, and FC3 layer. The input image is given to the convolution 1 layer. The forward pass of the model is applied to the second pool layer. Notice that there are two newer layers from the previous slide, the ReLU layer 1 and the ReLU layer 2, which comes into existence after both the pooling layers. So there is the convolution layer, the pooling layer, and the ReLU layer, and these three layers are repeated for the second time, in which the second pooling layer is given the forward pass of the model, and the transformation from the ReLU layer to the FC1 layer is where the application view is done, and the FC3 layer's output is given as the classification result. Before start, Before we start the training, we need to know for starting the training what are the requirements we need. We first initialize an instance from the model which we have already defined. We specify the criterion, that is the loss for the evaluation of the model. We specify the settings of the optimizer, and then we specify the way learning rate changes during the training. These four tasks can be performed by the four lines. The initialization can be done by the line model equal to sample network, initialization of the model. Then we define the criterion by using the cross entropy loss function. We specify and set the optimizer using the sgd command with the model parameters, with LR being 0.001 and the momentum being 0.9. We specify the learning rate by declaring a scheduler which has a step loss rate of optimizer, step size of 7, and gamma value of 0.1. saving best model parameter. We need to train the network for the specified number of epochs. Before training the process, we save the initial weight as the best model weight and set the best accuracy as 0. In every epoch, and after finishing the training process, we use the trained model to select the model which has the best performance on the validation set. Next we have the iteration over the training and the validation sets in every epoch. In every epoch, we either train the model or just use it for validation or evaluation. For training, we need to set the model to train mode, and for testing, we need to set the model to eval mode. For phase in train and validation, if the phase is train, we use, apply the train function to the model, else we apply the evaluation function to the model. Iterating the model over mini batch. We use the data loader which we have created in the previous slides to go through the data. What we get from the data loader are tensors for images as inputs and labels, and we need to transfer them to the device which we have created before. Phase here in this context refers to the train and test. For the inputs and labels in the data loader, that is the phase, the inputs are the inputs to the device, and the labels are the labels given to the device. Prediction and backpropagation. We zero the gradient before the start of a new mini batch. We then apply the forward function to get the logit function. We get the highest logic as prediction. We compute the loss based on the predicted value and apply backpropagation if we are in train phase. Summing all the loss of the batch with the loss values, we sum correctly the predicted values in batch with all the loss values. Finishing and iterating over the data in one epoch. When iteration over all the data is finished, then we need to compute the loss and save the best model. Using the scheduler setting, that is, the learning rate needs to be updated, and hence we use the step function to update the scheduler. Loss and accuracy needs to be computed at the end of the epoch, and the best model amongst these is saved. Test on the best model weight. We load the data for the test by transforming the test images, that is composing it, resizing it, converting it to tensors and normalizing it, and then load the data and get the data set. Testing the loaded data. We first set the model in evaluation mode and iterate over test data and compute loss and correctly predicted values for n number of epochs. And then we compute the loss and accuracy over all the data. Transfer learning. Transfer learning is something that we have done in the previous video lectures, but here is a recap. Most of the time, instead of creating and training a model from scratch, we can use the state-of-the-art models which have been trained on larger dataset like ImageNet. This process is called transfer learning. In transfer learning, in, for a pre-trained model, we have an old classifier which is given. We have an input which is given to a CNN layer, number of CNN layers, which gives an old classifier as the output. We extract the pre-trained CNN model, and in the new model, the same CNN layers give a new classifier as an output for the given input. Transfer learning example. Now let's say that we have a new data set which has two classes. We want to fine tune the state of the art model residual net, which has been trained on ImageNet on our dataset. We first get the pre-trained RES net, which is for a residual net, short for residual net. Then we get the number of features in the last layer. We replace the last fully connected layer with a new layer.